In this video, we are going to talk about multiple representations of functions, and our goal is to be able to create and analyze those representations in the context of a situation. This video is going to focus on the analyzing piece of it. So a functional relationship just tells us the relationship between two variables. So in this little animation, a dude is being shot out of a cannon, pulling a parachute, and coming back to the ground. So the independent variable in this situation would be the inputs of our function would be the time, right? How long is Cannon Man floating through the air? The dependent variable, the one that depends on another, which are the outputs in our function, would be his height. So we can create a representation to show Cannon Man's height over time. So I can take this, for example, and I can turn it into a graph. I can draw a picture to show how high he's going, and so on and so on and so on. Right? So now I've taken this animation and I've turned it into a mathematical representation of his height over time. Now my picture, my graph, isn't quite perfect for the animation, but it does show us some important pieces, right? It shows us how his rate is changing, it shows us his height. So we're going to talk about how I can take that animation, that scenario. I could create a graph to represent his height over time. I can create a table of points. I could create a story. And I can create algebraic rules, and I have two, just so you are aware, because there's a curved part of this function as well as a linear part of this function. So each of these pieces of these representations can tell us something different, but they all still represent the exact same scenario. So that red dot that just appeared on the graph is the point 328. It's his maximum height. So in the graph, it's easy for me to see that because it's the highest point on the curve. But I can also see that exact same point in the table, 328. I can see that same information in our story, maximum height of 28 feet. Now our algebraic rule, the way that it is currently set up, I have no idea what the maximum height is. However, I can still find this exact same point using my input-output relationship. For example, if I substitute 3 into my equation for the first one, I would end up with 28 feet, or should. Although that equation is an approximation because that's not exact. So we want to be able to analyze these representations. So we want to be able to talk about the variables. What do our inputs and outputs represent? The intercepts, where are they on the graph? How do we find them? Where are they in the table? And what do they mean in our situation? Tell me about the rate of change. And then tell me about the allowable inputs. Those are all pieces, key features that we can analyze from a function, and we can use different representations to do that. So, for example, we're going to talk about the variables. If I gave you just the graph, or just the table, or just the story, or a rule, how can I identify what those variables represent? Well, the independent variable, which are our inputs, if I look at the graph, I see that my inputs would be time. My dependent variable, the outputs, if I'm again looking at the graph, I can see it's the height off the ground. I can see those same exact variables in my table as well, time versus height. In the story, it's not as clear what our variables represent, but I could probably figure out that if I'm shooting a man into the air, I can represent or show a relationship between his height and time. The rule, however, this representation, without being defined, I have no idea what those equations represent, and I don't even know what part of the story they represent. So for this instance, trying to identify variables is not going to be as useful if you're just given an equation. We can also talk about the intercepts. So the y-intercept is always when x is equal to 0. On a graph, that's on the y-axis. So it would be that point right there. That's the point 0, 0. I can also see that same exact y-intercept if I'm looking at my table. I don't have to do any work. I just say, hey, there's the point 0, 0. I know that's got to be a y-intercept. The story, not a great representation. It doesn't tell me where the man is at 0 seconds. And the rule, because I'm on that curved part, I can always identify the y-intercept for every equation known to man if I substitute 0 in the x spots and I solve. So if I do that, I end up with y equals 0. So the easiest representation to use for this situation would probably be the graph or the table. You don't have to do any work. You can just see where it is. So that means at 0 seconds, Cannon Man is 0 feet off the ground. If I want to find the x-intercept, that's always going to be when y is 0. Easy to see on a graph. That's the x-axis. Those 2 points right there, 0, 0, and 10, 0. If I look at the table, I can only see that 0, 0. So the table doesn't give me all of the information that I need. In the story, it doesn't tell me at all anything about the x-intercepts. It doesn't tell me when he comes back to the ground. It doesn't really tell me when it starts. So the story in this instance, not a great representation to use if you're being asked to identify those intercepts. For the equation, it's the second one in this situation because it's on the straight part, we can find any x-intercept for any equation ever by substituting 0 in for y and solving. We end up with x equals 10. So that means at 10 seconds, he's 0 feet off the ground. So again, in this scenario, the graph is going to be the best representation because it's a visual representation of Kahneman's height over time. Doesn't mean you can't use the other representations, they're just not as efficient. We can also talk about rate of change. Rate of change we're looking for right now, is it constant or not constant? So not constant, we see the things that are curved. Hey, from that point on my graph, I can easily identify that it's not constant. In the table, I can easily identify for this set of time, I have a not constant rate of change as well. The story doesn't really give me much information. And for my rule, I can see, well, that's a quadratic. And I know from my previous knowledge that quadratic functions do not have a constant rate of change. If I ask you, so that means from 0 to 5 seconds. If I ask you, well, where is my rate of change constant? We're looking for straight lines and linear functions. I can see on the graph that's a straight line. So from 5 seconds to 10 seconds, I've got a constant rate of change. I can see from the function for that part of my graph, it's a linear function. So I know that is also a constant rate of change. The table doesn't give me any information past 4 seconds. So it doesn't really tell me much about the rate of change. The story, I can pull out some pieces of information and make assumptions, but without actually having some mathematical data to support my thinking, I don't necessarily know that there's not a constant rate of change, or there is a constant rate of change or not. So the last thing we can talk about are the allowable inputs. What makes sense in our situation? What can I put in for our x values? Well, we know that our inputs in this scenario are time. And the easiest way to identify what makes sense is think about, well, how does time operate? Can't have negative seconds, so I know that my time has to be positive. I can see from my graph that time starts at 0. From the table, time starts at 0. And from the story, again, we're just using what we know about time, can't be negative. The rule, however, gives me no information about our allowable inputs. We also can see from the graph that he hits the ground again at 10 seconds, so our allowable inputs for this scenario would be 0 to 10 seconds. From the table, I don't really get much information past 4, so it doesn't really tell me a whole lot. So the graph is one of the best ways in this situation to talk about those inputs. Although all of these represent the same situation, they all give us different pieces of information, which is how multiple representations work.